Okay, g'day all, welcome to another video. G'day all, welcome to another video. So today I wanted to talk about the shift instructions in assembly, and I've got a little introduction here. I called it, Bro, Do You Even Shift? Clever. Alright, so we're exploring 64-bit shift instructions here. A lot of these will work with 32, 16 or 8-bit operands as well, but the instructions that we're looking at today are SHL or SHUL, shift left, shift arithmetic left, which is the same thing, shift right, shift arithmetic right, rotate left, rotate right through the carry, rotate left through the carry, and then the double precision shifts as well. Okay, so we might just start with the shift left and shift right instructions. The first thing I want to say is that SAL, shift arithmetic left, is not really an instruction. It leads to exactly the same machine code, so you really just want to stick to one. Usually you want SHL. Yeah, so SAL is just the same instruction, but a different mnemonic for exactly the same thing. Okay, so if we jump over here to C++, I've got a little bit of a demo here. Extern C shift test, that's the function that we're just about to have a look at in assembly when we run the instructions. And we've got this print bits kind of business just here, which is the same as last time, only this prints out a 64-bit operand. And it also prints out the carry, since the carry flag might be interesting to us today. And down here in my main method, I've just got an unsigned long. That's a 64-bit unsigned integer, and I've set it to some random value. I initialize the carry to 0. We print out the bits, and then there's a cin.get. But what I really wanted to do today, I want to see if this works. So I wanted to run these instructions over and over again, and then if I hold my hand on like the enter key, it should appear as though it's animating. It's probably the lowest budget animation you'll ever see, but let's see if this works. So shift test is really what we're running, and if we have a look over here in assembly, I should mention also that it's Queensland, and it's the middle of summer. It hasn't rained for weeks, and to stop the noise, I've turned off the fan. There's no aircon, and the window's closed, so I can tell you now it is hot. Right, shift test. Okay, so all of this business up here is just setting stuff up. I clear the carry flag, I move the parameter into RDX, and here's the actual instruction. So shift left is what we're checking first of all. If I run this, we should get a bit of an idea what's going on. Okay, so here's the parameters as they start. So the carry flag is 0, and this RDX parameter just here, this is that number that I set in C++. This is that in binary. Okay, but if I hit enter, you should see that all of the bits moved to the left, one space. And if I hit enter again, they moved again. And if I keep hitting enter, you'll see that they just keep moving to the left. They're moving one space each time I hit enter. That's because this is shift left, and the parameter just there is a 1. So there is something interesting about a lot of these 1 shifts and rotates. There's a second instruction it was actually faster at one point, but I think they run at the same speed. But if you have an immediate operand just here and it's 1, then you'll get a special version of the instruction that also affects the overflow flag, the OF. So the overflow flag after a 1 shift will tell you if the sign changed. Would you believe that? Okay, but for all other shifts, say a 2 just here or a 124, it's not going to affect the overflow flag, only the carry flag. All right, but if we keep hitting enter, we should see what the carry flag does. So you'll notice that the carry flag hasn't done anything so far, but if we keep hitting enter, you'll see these little ones march to the left, 1 space at a time, all the way up until the end. And then if I hit enter again, there you go. So the final bit shifted out of your operand becomes the carry flag with a shift left. Yeah, easy as that. Okay, but that's a shift left. And if you change this number just here, this is the amount to shift. So if we make this say 5, then all of the bits are going to shift 5 to the left each time. Yeah, you see that? They jump 5 positions to the left. So here's my 1s just here, and now here they are, 5 positions to the left. Nice and easy. Okay, so that's a shift left. If we move over to shift right, and we run it again. Okay, so shift right is pretty much exactly the same thing, except the bit string is going to be moved to the right instead of to the left. So if I hit enter, they should all jump 5 spaces to the right. Yeah, there you go. jump 5 spaces to the right. So you'll notice over here that the carry flag just then was set to a 1, which means that the final bit shifted out on the right-hand side after this 5-bit shift was a 1. Yeah, so just like in the left shift, the right shift, that carry flag will represent the final bit, which was shifted out. A 1 in this case. Good stuff. Maybe I should talk about how we saved the carry flag. So I was wondering if there is a quick way to copy the carry flag after an operation. I couldn't think of one, but I went with a cmov-c. So that's a conditional move just there. And you'll probably have that in your CPU. I think everything since about the Pentium 4 days or something has cmovs in it. But yeah, if you can think of a quicker way to grab the carry flag other than these 3 instructions just here, maybe leave a comment below. I'd be interested to hear. Okay, so that's the shifts just there. I should say that the shifts are... The parameter that you pass is actually ANDed with 63. So if you try and shift, say, 64, if you AND the value 64 with 63, you'll get 0. So that's not going to shift at all. If we just hit run, you should see that it doesn't do anything. Yeah, see, it doesn't shift at all. If we go 65, you should see that it shifts 1 now. Yeah, so that's the same as a 1 shift. So that is something to be aware of, is that the shifts and this parameter just here with 63. If you're using 64-bit shifts, it's ANDed with 31 if you're using 32-bit shifts. But the weird thing, I think, anyway, that you can shift 16-bit operands 16 bits. I don't know. Go figure. Weird. That's assembly language for you. And the other thing that I want to mention is if you want to shift a variable amount, this is so weird. This is so weird. But it all comes back to the way that the instruction sets were invented. The first instructions that were invented were those single shifts. So something like that. Yeah, with a 1 parameter just there. You never used to be able to shift more than 1. So that kind of explains why that's a special instruction. But another interesting thing that we've got, I guess because of legacy reasons, is that if you want to shift by a variable just here, the only variable that you can use is CL. Yeah, so you can't use any memory operand. You can only use CL. You can't even use any other registers. It has to be CL. So you could do something like this, mov CL and 5, and then have CL just here. And that's going to shift RDX by 5. Obviously, that's pretty handy if you want to change the amount that you're shifting. We will have a look at the end at some of the costs of doing this sort of thing. So using a variable just here is not free. It's going to cost you in performance. But yeah, like I was saying, you can't have other variables here. So if I use AL, for instance, and try and run that, it's just going to say, nah, mate, that's got to be CL, dude. Invalid instruction operands. Yeah, it puts it quite abruptly. Those instruction operands are invalid. But CL, quite valid. It doesn't do anything, but quite valid. It would do something. It's just that RCX is actually the parameter that I'm pointing to, so we can't change CL as it happens at the moment. But yeah, I think you get the idea. If you want to shift by a variable amount, you've got to use CL. Okay, so the next instruction, what else did we want to say? First, what do they do? Okay, so the rotates. The rotates are actually, before we go on to... So the next instruction that I want to talk about is SAR, or shift arithmetic right. So shift arithmetic right is similar to the other bit shifts, except with the other bit shifts, what comes in from the other end is zeros. With shift arithmetic right, what comes in from the other end is actually the carry flag. So if we just get rid of that and we change this to SAR, we get rid of that and we change this back to 1. Okay, so we're back to our shifting now. If I hit run, this should pretty much perform exactly the same as before, just performing a normal shift right. So you'll see over the end here that zeros have come in to replace whatever was shifted out. But if we change it to a negative number, this is kind of why it's called arithmetic right. If we change that to a negative number, then what you'll see with the arithmetic right shift is that the 1s come in from the other side. Yeah, so that your number stays negative. Whereas if we were using a sugar. If we were using a regular shift right, it's not ones that come in on the other side. Look at that. It's zeros. Yeah, so if you're dealing with signs, numbers, and you're trying to do shifts, then you're going to want the arithmetic right shift. With the left shifts, it doesn't matter. Yeah, just use SHL both times. But you can do SAL. It's just a different name for the same instruction.